Next year?
What is it?
No? Okay, it's fine.
What did you say? Yeah, it's Sean. I want to work with Sean.
Sean. Yeah,
You might do it?
Yeah, sure.
Wait, what are you doing? What is it?
Senior design. Right now.
Well, yeah.
Well, why don't you tell them, hey, where's yeah, why don't you tell them what you're working on right now?
Okay, yeah, so what we're doing is, Jesus Christ. So our current thing is we're trying to generalize a tensor radon transform to, like, not necessarily just ADS space, but like generalizing space-time quantum information dualities to different structures of space-time.
You just said a lot of words.
Real dick. Basically, we do real whack tensor math and have a great time doing it.
Well, I know what a tensor is now, so I won't.
You know what a tensor is?
Yeah, I could be into that. I also don't have a senior design yet. I could be in.
Okay.
But I don't know
that's-
if I'd be useful. I would just be fun.
It will be fun. All right, that's what I need to know. Thank you. All right, let's get started. Because I got a lot to cover and we're recording it. I'll edit that out. But anyway,
Can you edit it just to the point that it says I'll edit that out? So like people will be wondering while
yeah, of course. I will. Yes, I'll start it right now because I can edit that out. Anyway. All right, folks, pay attention.
Josh.
Turn your ass around. Pay attention. We're not going to edit that out. All right. Okay, so today is gonna suck.
Yeah.
Today is so technical it sucks. Okay?
What if I like technical?
Well, if you like technical, actually that's true. We've discovered that there are kids in Physics 100 who need an explanation of what's going on, you know, diagrams, pictures, and then there's kids who just want math. Okay? Well, today is gonna be math. Very little pictures. Well, there'll be some, but anyway, okay. So, but what we're going to do today is we're going to basically look at and consider, hey, pay attention, damn it. It's hard to get your attention. We're going to look at and consider solutions to the Dirac equation, okay? And we're going to do some comparison to solutions to Spinor equations in 3 dimensions. But there's going to be a lot of technical detail in today's discussion. So you should all know what the Dirac equation looks like, and my first solution that I'm going to write down is going to be a solution for a particle at rest. So if a particle is at rest, then we know that the spatial derivatives of the spinor are all going to be 0. And this is just specifying that the momentum, the spatial momentum is 0, which of course you can see because of the interchange of derivatives with the 4 momentum if you want to turn this into an algebraic expression, which we're going to do. The 3 spatial parts of this correspond to the 3 spatial parts of this, which of course are the linear momentum. So if you want the linear momentum to be 0, i.e. you want the particle at rest, then you need the 3 spatial derivatives to be 0, and there they are, okay? So if you do this, then the Dirac equation actually simplifies to the following form: gamma 0 d0 psi plus mc over h bar psi equals 0. Okay, you only use one of the gamma matrices, all right? Now, if I actually write out what gamma 0 is, and go ahead and take this derivative, then this is going to become 0 minus I 0 d psi by dct. Okay, that's what the derivative with respect to time looks like, plus mc over h bar psi equals 0. And of course, psi is a 4-component spinor vector, or 4 complex components. And remember, these are 2 by 2 matrices each. And this is minus I times the identity. Okay, so I mean, if I got to write it in, I'll write it in. I'm not afraid. Okay, so here we go. if we just stick in this guy right here, take the derivatives, then we're going to end up with a system of equations that look like this: minus I over c d psi dt plus mc over h bar psi 1, and this is 3 equals 0, minus I over c d psi d4 dt plus mc over h bar psi 2 equals 0. And all I'm doing is multiplying this matrix times this, the derivative of this vector, and then adding on the coefficient times the vector. And last but not least, so 4 equals 0. Okay, so does this make sense where this comes from? And it's pretty straightforward. All I'm doing is I'm writing this thing, I'm writing down all the different equations that correspond to this matrix expression. Okay, so these are going to afford us 4 solutions. And they're going to be labeled in the following manner. And I'm going to label them all rest solutions. E to the minus I mc squared over h bar times t times 1 over root 2, 1, 0, 1, 0. Okay. Oh, wait a minute. How many components does that have? Yeah, this is a component of the spinor. Okay, so it's a complex number. So what is this? It's just the label of the solution. It's the first solution. The first solution is a 4-component spinor. There you go, 4 components. Okay? And they're complex because of this coefficient. So I just want you to realize these subscripts mean something different than these superscripts, which I'm putting in parentheses to encourage the point that these things are different solutions. They're not different components. Okay, this looks pretty nice. This is pretty sweet. And then it gets a little weird. Okay. What's the weird difference between these solutions? Let me draw a card. Stephen.
We have a positive I and one of the spinors is negative.
What's so weird about it? Huh? It's just different? It's just different. Does this term look familiar? Maybe we'll rewrite this term. Maybe we'll rewrite it a little bit. These things are at rest, right? So how much energy do they have?
MC squared.
mc squared. So actually, this right here is e to the minus I e over h bar t. You ever seen that before? What does that describe? It describes the time evolution of this system. Okay? As you tick the clock forward in time. What about that? Okay, well, maybe the energy is negative. But how do you get the energy to be negative?
Tachyons.
We're not going to talk about tachyons yet. We will. Yes. So the original way that this was thought about, and this was by Feynman and Stuckelberg, was to interpret this as a particle moving backwards in time. Okay? So it's a positive energy particle, but it's moving backwards in time, so T would be negative. Okay? However, eventually the interpretation came around that this is in fact antimatter. Okay? So the psi 3 and the psi 4 solutions are actually describing antimatter, and the psi 1 and the psi 2 solutions are describing matter. All right? And we're going to have some, you know, some evolution of the ideas of antimatter throughout this course. But this is, and I promised you this last time when I said, this thing, if you do the Wigner classification, you know, you pick a momentum or you pick a momentum and then you find the transformations which lead this invariance. So we pick the rest frame. We have SO3 rotations, which you can do on the momentum vector. And if you classify things under SO3 rotations, then spin a half has 2 states, up and down. But this thing had 4 parts. And it had 4 parts because it has matter, which has up and down, and then it has antimatter, which has up and down. And that's where the 4 parts came from instead of the 2. So this thing is smart. It knows about antimatter, and it contains the description of antimatter. Yes?
So with it describing antimatter, does that not still, like, this equation still seems to be implying some kind of backwards time evolution or negative energy or something?
Yeah, and we're going to use that idea when we construct Feynman diagrams. But there's another interpretation which we'll give it later on. But when we do Feynman diagrams, if we're doing our Feynman diagrams where the evolution in time is to the right, then if we want to have a particle, then we just draw a line with just the representation of the particle's propagation and an arrow pointing to the right. And the only thing you have to change if you want to describe an antiparticle is that. Okay, but we'll give it another interpretation later on. But this was a useful interpretation, Ode to Feynman, for working with them in his diagrams, which we'll also learn about. Okay, so all right, so let's see how the spin story works out for this quickly, because in the next discussion, the spin story is going to get a little crazier. So remember, SZ, the spin along the Z component operator, is defined as h bar over 2 sigma z 0, 0, sigma z. Okay? And if I actually plug in what the sigma z's are, this matrix comes out to be 1, minus 1, 1, minus 1. Okay? And this, of course, acts on a 4-component spinner. So if I hit psi 1 at rest with the sigma z operator, Brandon. Where are you, Brandon? He's not here. Chance. Yeah, chance. What do I get if I hit psi 1 at rest with sigma z?
You get the same thing except the vector's going to be 1, 0, 1, 0, so same thing.
I'm going to get the same.
Oh, except the h bars with an h bar or h bar over 2 term.
Yeah, so this is a spin along z. What are the possible values of spin along z?
No, it's positive, negative,
Positive, negative.
and
What's the eigenvalue?
1, negative 1.
You're measuring the spin along z, and this is a fermion. So how much spin does it have? That it have?
1/2.
1/2 h bar. H bar has the dimensions of angular momentum. So this ends up coming out as h bar over 2 psi 1 rest. Okay, everybody see that? We good? Okay. What if I hit side 2?
You get a negative.
Yeah, you get a negative because this thing is non-zero in the second and fourth slot, and in the second and fourth in the matrix you have negatives. Okay, what about side 3? Yeah, it's another negative. And then side 4 is positive. Okay? So what we see is that if we want to describe or classify our particles in terms of their spin along z, then we have a spin up along z, a spin down along z, a spin down along z, and a spin up along z. Okay? All right. Oh, Sean is next. You must be so happy.
I'm thrilled.
You're thrilled? Good, good, good. Okay, so maybe I'll let one of these solutions hang out. I'll let Psi1 rest hang out. But how useful do you think it's going to be for us to do, physics with only particles at rest?
Not very.
Good, not very. So we need to find a solution where things are moving. Now, when you want to handle things which are moving, you think they should be moving in a particular way? I mean, do you think we should look at particles that are doing this? That's mathematically easy to describe, correct?
Yeah. It's a little farmer feels like a back under and stuff.
This sucks, okay? So we want to describe a moving state, a moving particle, and we would like a really clean description. What are y'all doing? All right, put it away and hand it to me, damn it.
It's kind of spelled like that. I spelled it wrong.
Okay, what is the cleanest description of a moving something?
It's going to be a plane wave.
It's a plane wave. Yeah, you think about plane wave. It's only got one thing. It's the direction that it's moving and how fast it's going. Damn, let's do a plane wave. Yes, so we're going to make a plane wave approximation. And what's interesting about a plane wave approximation is that you completely forgo where the hell the particle is. And the only thing you let yourself know is how fast it's moving. You guys are so sad. All right. And when we do a plane wave, what we have in mind is it's just a series of these infinite wave fronts perpendicular to the motion. So you don't know where the particle is. Well, these are infinite. Okay? So why do we have to give up where the particle is?
Heisenberg answer.
Yeah, it's the uncertainty principle, because what two things can't you know simultaneously?
Position.
Position and momentum. Okay, so with these plane waves, we're going to be able to specify the momentum exactly, but we're going to completely give up the position. Who cares? All right, when we do an experiment, we don't take a particle and we know where it is and how fast. We don't do this sort of jumbled measurement of a little bit of each. We just say, damn it, I'm going to create these particles with a certain energy so I know how fast they're going. I don't give a shit where they are. And I'm going to smash them together and then let them spit stuff out. So we're really interested in the momentum values of these things. And so a plane wave description is actually the most useful in terms of doing calculations to be compared with experimental results. So, plane wave. A plane wave, you should be familiar with this, has an amplitude and then it has a propagation factor. And then we're going to have this piece, which is the four-component spinor part. Okay? But this is the part that's really going to be propagating this thing along as a plane wave with well-defined momentum. If we plug this into the Dirac equation, now this isn't the solution because we have to figure out what all the details of this solution look like. But if we plug this into the Dirac equation, then the Dirac equation reduces to this. Oh, sorry, no, that's not the Dirac equation. That's the, this is the substitution of derivatives with the momentum. This is the Dirac equation. Then we have the Dirac equation becomes the following. I h bar gamma mu k mu minus mc psi equals 0. Okay? So this is the Dirac equation. And can Sean, I want you to help me for a second. You know, the Dirac equation, what kind of equation is the Dirac equation? Don't look at that, look at the original Dirac equation. It involves this thing. What kind of equation is it? It's a differential equation. And how easy is it to solve differential equations?
Depends on the differential equation.
It depends on the differential equation. Generally, though, they suck. What kind of equation is this? Do you see a differential operator in there?
No, I do not.
What kind of equation is it?
Just, not sure.
You want to phone a friend?
Yes.
Phone a friend.
Algebraic.
It's an algebraic equation. Okay. So we've converted the differential equation into an algebraic equation. Okay? And you can do this because you're taking the plane wave solution. Okay, so this is one of the huge simplifications afforded to us by taking the plane wave version of the solution. All right, now we're going to be able to identify the parameter k mu with the spatial momentum, sorry, k upper mu. So k mu is going to be able to be plus or minus 1 over h bar p mu. Okay, and this, it takes a little bit of work to show this, but this relationship is obviously simple. This parameter k mu that appears here can either have the value of plus or minus 1 over h bar times the spatial momentum. Okay? Or sorry, the 4 momentum, this p mu vector, not a spatial vector. And if we solve this, plugging this in, then we get the following 4 solutions. And these are obviously going to be a little bit more complicated than the at-rest solutions. Okay, this term right here is just taking this prefactor and doing this replacement. Okay, so this is not really anything new. It's just rewriting this term. Okay, this is where we're going to get something new. Anybody got a good joke?
We already went over this one.
I know, we're going through it again because it's going to take me a minute to write this thing up there because it's a little bit on the long side. So, whoever has a joke, go in front of the camera and tell the damn joke. You guys suck.
We could like bring a puppy. We could like bring a puppy or Bruce back to us. Just have him run around.
Show what's
Was
going
Rachel's dog still?
Do it.
That was like
Just because I don't
Nobody's telling jokes, you're just chatting.
Joel, why are you crying?
This is so...
Because we saw a picture of a bratwurst. It's pretty funny. It's actually just a website. Yeah, it's pretty funny.
You showed him a website, which is a picture of a
I
bratwurst.
looked up a Weierstrass function, and just because the guy's German, it popped up a picture of bratwurst.
The first thing that it clicked on was just some company that was selling That's all it was.
like
a Cyrus company.
Hey, YouTubing people. You like our brats?
Subscribe. Just smash that like button.
That is continuous.
Subscribe and ring that bell for notifications.
Okay! Shut your pie holes.
Are you finally?
Are we able to tell jokes
Okay,
now?
No, you can't tell a joke now. It's too late. You're screwed. All right, here we go. All right. Let me see whose card is on the top. Oh, look at that. I think I'm going to leave this on the top for a while. I'm going to ask Joshua a few questions. Maybe every single question for the rest of that 45 minutes. So, Josh.
Yes.
Do these reduce to the at-rest solutions if we take the momentum to 0?
I don't think so.
Yeah, you're going to prove it in your homework. They do, though. It's almost trivial, but you will take at least one of these.
Excuse us.
You will take at least one of these, put in the spatial momentum being 0, and show that it completely reduces to the at-rest solution. Was that surprising to know?
It's pretty surprising.
It shouldn't be surprising at all. These are the solutions for an arbitrary momentum, including 0 momentum, which is what this is a solution for. So you'll prove that in your homework. By the way, you've got a homework assignment which is largely based on the content of this class, and it's due Thursday. So and I'll be there the whole time tomorrow, except I got to run and grab my chemo pills from the store because they were supposed to come tonight. They're coming tomorrow. But anyway, yes. Go ahead.
Do the superscript you're using for 1, 2, 3, do those match over to each solution?
Yes.
The at-rest solution should match each one?
Yeah. That's kind of. Okay, so
Offhand question.
yeah.
What kept us from just taking those rest solutions and boosting?
Very, very interesting question. Extremely interesting question. Which I think you're going to do in your homework. But thanks for asking. Thanks for asking. Okay. Yeah, I'm pretty sure you have a homework problem doing that.
Just in case we don't.
Yeah, no. But so what Gabriel suggested is incredibly smart, because you might say, oh, well, why didn't you start with this? Because that's a special case of it. But instead, you could have started with this and then just said, okay, if I want to give this momentum along the z-axis, I just boost this along the z-axis. Okay? And the only thing you have to figure out is what is the 4x4 boost matrix as defined for spinors. Okay, which isn't completely obvious. It's not the boost matrix you use for vectors. It's a boost matrix for spinors. Okay? But it's not that bad.
Find those?
Huh?
Did we find those at some point?
I think we did. I think we wrote down the boost matrices for spinors.
Sigma units? Whatever?
Yeah. Okay, so, all right, so some notation, and this is a notation-heavy day, sorry about that. Another way that we can write these, and I don't know why I didn't say room over there, but I didn't, is, well, actually I'll do, yeah, I have to do it this way. E to the I P mu x mu over h bar u1. Yeah, so we'll just say this. We'll say I. Okay? So we can do a U1, we can do it with a U2, and then if we do 3 and 4, then these exponential terms are going to have a minus, and then we'll have a U3 and a U4. And in that situation, actually, sorry, I'm getting ahead of myself. I'll just write these things down because I'm trying to be efficient with what I'm writing on the board, but it's somewhat important for you to see it. So U1 and U2 describe particles. And for antiparticles, we instead like to use V 1 and 2. Because antiparticles are different states. So instead of doing 1, 2, 3, 4, because after all, 1, 2, 3, 4 notation kind of implies that these are the 1, 2, 3, 4 components of the coordinates of space-time, which they're not. Now we can say 1 and 2 for particles, 1 and 2 for antiparticles. So this notation makes it a little clearer not to think of this in terms of coordinates and then to group it in terms of particles and antiparticles. Okay? All right. Now, here's the important observation about this. And this is probably one of the most fundamental things, and it's going to lead us to some interesting things to develop. Do you remember when you got to Spinors in quantum mechanics? How many of you remember? Raise your hands. How many of you forgot? How many of you never saw it? Damn. Okay. All right. Well. Okay. That's fine. That's fine. That's fine. I'm just. Okay. Damn. In non-relativistic quantum mechanics. Okay. In non-relativistic quantum mechanics, the wave function of a state can be written in the following manner. Okay? Where, pay attention, this part of the wave function is describing either the motion or the position. This is the standard solution to the time-dependent Schrodinger equation. And this part of the wave function is telling you about the spin state. This is a two-component object, plus or minus if you want to know what its z component is. Okay? But here's the very, very important observation. All spatial information is contained in this part of the wave function. This is just a vector of 1, 0, or 0, 1. This doesn't contain any information about where you are or how you're moving. Okay? Does that make sense? These are clearly not that way. These solutions, the spinor part of it, contains inextractable information about your motion. Unless, of course, you're doing what? Unless you're at rest. Because if you're at rest, then that's the spinor part of your motion. You can extract any energy information, which is just that you have a rest energy of mc squared. Okay, so when you're at rest, you can kind of break it up like this. But in general, when something is moving, you can't. When something is moving in non-relativistic quantum mechanics, you can still break it up like this. Okay? All right. Now, we might ask about SZ on these. Let's see, okay? So if I do SZ on psi1, that's this psi1, not got the rest symbol, then let's see. So if I'm going to use my SZ here, if I hit this with SZ, then I'm going to have h bar over 2 a e to the I p mu x mu over h bar times the quantity e over mc squared minus pz over mc px over mc plus I py over mc. It's 1, 0. Huh. Everybody follow that? I mean, I'm just hitting this term with +1, this term with -1, this term with +1, this term with -1. So this changed sign. Pretty straightforward, right? What is it not? Oh, I'll draw a picture. Oh, look at whose card is on top! Joshua! It's funny because Sarah's right under you, but she's going to stay under you. What is this thing not?
It is definitely not a constant.
Yeah. And?
It's not h bar over 2. It's got that in it.
Yeah. You want to phone a friend?
It's not of the form of any of the solutions.
Ooh. Well, a more simple observation is that this is definitely,
It's not like a multiple of the first. Yeah.
psi1 is definitely not an eigenvector, eigenspinner. Psi1 is definitely not an eigenspinner of SZ. Okay? Which is a bit weird. Because in non-relativistic quantum mechanics, if I do SZ on this, I'll always get an eigenvalue back. Okay? But here we find that, yeah, it's not an eigenvalue of psi z, or of SZ. And neither are any of the other ones. Okay?
What are they?
I don't know. I mean, this is deep stuff. I really don't understand it. It's really deep. It's super deep. But, hold on. Now, let's think about this for a second. We're picking SZ, so we're defining a three-dimensional coordinate system. And then we're wanting to know the component of spin along that axis. Now this is a plane wave particle, right? So it's got momentum in some direction, right? What is the direction of the momentum in these solutions? No particular direction. So this is just some random ass momentum vector. Okay? Now if a particle is moving along a path with fixed constant momentum, and we're going to come along and we're going to try and describe its state, maybe it's not the best idea to pick a randomly oriented coordinate system. Maybe what we should do is we should line up one of our coordinate axes with the momentum. We can do that, right? You're always free to pick coordinates. So if you've got a particle that's actually moving, just pick a coordinate system so that one of them is along the direction of motion of the particle. Does that seem reasonable? Do you think it's going to simplify things?
No.
Hell yes, it will. Okay? So let's see what happens. So if I choose my momentum to only have a z component, okay, then if I come in here, this term is what? Zero. So it only leaves this term, this term. So if I do that, and I do SZ on psi1, then I have h bar over 2, 1 minus 1, 1 minus 1, times a e to the I p mu x mu over h bar times e over mc squared minus pz over mc, 0, 1, 0. And let me just pull a oh, Josh. What's this going to give me when I hit this with this?
Yeah,
What's it going to give you?
an eigenvector,
An eigenvector with what eigenvalue?
h bar over 2.
Yes. You're warming up. Good, Madison.
Aren't you not allowed to, like, isn't it like illegal to be able to specify two components of the momentum at the same time? Like you picked x and y to be 0, but can't you not know x, y, and z? Or am I conflating them with something?
So with linear momentum, we have that pi, pj equals what? 0. With linear momentum, you can fully measure px, py, and pz.
Okay.
You can't do that for the spin or for angular momentum, okay? Now, you also can't do the x position and the x component of the momentum, but you could do the x position and the y component of the momentum. Okay? All right. Oh wait, what about the other ones? Are they all now SZ eigenspinors? Well, let's look at it. Here, this term goes to 0 and I'm left with this and this. Is that an eigenspinor? What's the eigenvalue? Negative h bar over 2. Here, this term goes to 0 and I'm left with this and this. What's the eigenvalue? Negative h bar over 2. Here, this goes to 0. What's the eigenvalue? H bar over 2. Okay? That's the same series that we got on the rest eigenspinors. Okay? Oh, there's a word for this. In non-relativistic quantum mechanics, you just pick the z-axis, because anything works. You pick the x-axis, the z-axis, the y-axis. You don't have to worry about how that z-axis lines up with the motion. Here, though, we are going to talk about the component of spin that is along the direction of motion. And the name of that concept is helicity. We have positive and negative helicity. So it'll be often the case that I'll draw a picture of a particle moving that way, and I'll talk about if it has positive helicity or negative helicity. Does this make sense? Helicity is simply choosing the axis along which you want to specify a component of the spin. Because you can only pick one, right? You can't tell me the spin along the momentum direction and the orthogonal direction simultaneously. That's not allowed because this is angular momentum. Okay? So at best we can specify one of them. And we're just going to pick the component along the direction of motion. And the answers are positive and negative. Okay? I want you to absorb that because I'm about to take it and screw with it pretty badly. Does the notion of helicity make sense? All right, here we go. It's going to hurt just a little bit.
Don't tell us that.
Okay, so let's take helicity and let's explore it for a couple of minutes. Yeah. Well, I'm just going to erase all this. I'll get rid of it. Okay. So okay, so helicity is almost like categorizing things by their spin along the z-axis. There's one tiny little difference. Okay? So let me give you a couple of arguments for why these things are the same. So for example, suppose you have a particle that has SZ equals plus h bar over 2. All right? So we have a coordinate system here. And in measuring the z component of spin, we found that it points in the positive z direction. Okay? Let me ask you a question. Let me grab a card. Oh, it's Josh. Josh, is it possible to change that without touching the particle?
Without touching it?
Yes.
I'm going to say no.
Can you change this by touching the particle? And by touching it, I don't mean... Holy, never mind, screw what I was teaching you, I just checked that. Yeah, no. No, you can use a magnet. Magnets, these are charged particles with a spin, so they got a magnetic dipole. You send it through the magnetic field, and the magnetic field will make it do things. And so you could probably flip this over. Yes?
There's like some funky wonky like fill.
No, it's completely, I can take
It's
this
like-
and I can flip the spin over
Yeah.
by letting it interact with a magnetic field or some other means, okay? Now, can I make this negative without touching it? You got a sea of people behind you who are all like, yeah? Oh, yeah? Oh, you guys supposed to stop. What do you think?
Mayhaps.
Huh?
Yeah.
Well, let me ask you something. Why does this have positive, why is this a positive eigenvalue? Because it's pointing
Up
up.
with it.
Yeah. What would you do? Yeah, why don't we consider this? Come on. Nope. Okay? What's the spin of this same particle that you haven't touched in this coordinate system?
Negative h bar over.
It's negative h bar over 2. Okay? So by flipping our coordinate system, we can reverse the sign of the spin. Make sense? Does that make sense to everybody? Yeah, it's pretty sensible. Okay, fine. I said helicity is like it, so what about helicity? Well, let's see. If I have a particle that's moving in this direction, and it has spin in that direction, oh wait, hold on. Now you're realizing it. With SZ, the direction is based on a coordinate system, which is this arbitrary thing you pick. But categorizing things by helicity, I don't have to specify a coordinate system in order to tell you the sign of the helicity here, do I? What's the sign of the helicity in this case? It's positive. So helicity is sort of a little bit disjointed from the choice of coordinates, which is a more robust way to work. Okay? Now, can I reverse the spin of this? Can I literally flip the particle over? Yeah, probably. But can I flip the particle, or can I reverse the helicity without touching the particle?
Couldn't just boost it?
Boost it?
Boost it? That's such
Boost it in what direction? Yes. If a particle is moving in this direction, oh wait. So if I am in this frame S and I observe the particle moving to the right, if I wanted to reverse the direction of its motion, which direction should my frame boost? To the right or the left? To the right. Okay? If I go to a frame which is moving to the right faster than this particle, then this particle will be moving to the left. Okay? What's that going to do to the spin? It's not going to do anything to the spin. So in the frame here, we now have the particle moving to the left, the spin to the right, and what's the helicity of that? It's negative, okay? So I'm just showing you that in the same way that we could choose our coordinates differently through a rotation, we could reverse the spin component here. When we work with helicity, we can also change the helicity component, but this time we do it with a boost. Make sense? Does this make sense? So this is why helicity is very much like SZ. But let's focus on this word for a minute. Can you always do this? Can you always do this? When can't you?
Move at the speed of light.
When the particle is moving at the speed of light. Yes?
Is there like weirdness with the like You can think about a sort of continuous boosting where like it becomes 0 for a minute before it flips negative. That seems weird, right? Like, because if you're going from it being that way to them not matching, that sort of.
Yeah, you'll be in its rest frame.
Oh, yeah.
And identifying helicity in the rest frame of something is pretty weird.
Yeah.
Yeah.
Okay.
But in the rest frame, you can just do SZ because that's an eigenspinor of SZ.
Okay.
Yeah. Okay. But I want to make sure everybody just heard the point we just made. All of this is the same for helicity and SZ except when we're dealing with a massless particle. When we have a massless particle which must travel at the speed of light, if it has spin, then it's either going to have spin plus or minus h bar over 2. Or sorry, its helicity is going to be plus or minus h bar over 2. And that is a quantity which is intrinsic. It cannot be changed. So you know what we could do? For massless particles, why don't we, let me see where I labeled it. Oh, I didn't label it. I'll label it in a minute. Oh, yeah. There it is. For massless particles, we can actually think of the positive helicity as one particle and the negative helicity as a completely different particle. There's no reason why those have to be two different states of the same particle. It has to be the case if the particle has mass, because you can take a positive helicity and change it into a negative helicity. It's the same particle. You're just changing the relative motion that you have with it. But if a particle is massless and it has positive helicity, nothing in this universe can turn it into negative helicity. So you might as well call the positive helicity massless particles distinct from the negative helicity particles. Does this make sense? Okay, we're going to keep beating on it. All right, so let's see if we can follow this or trace the roots of this back in Wigner's classification. Yeah, remember that? Okay, so in Wigner's classification, what we did was we took the 4-vector momentum and we went into what space? Or what frame? So remember, in the Wigner classification system, you take a given momentum and then you ask what transformations can you make on the momentum that don't change it. So what frame did we go to? We went to the rest frame, okay? Oh, E rest over C, this is MC, 0, 0, 0. And then we realized that you could do 3D rotations. And then based on being able to do 3D rotations, that meant that we can use the non-relativistic quantum mechanics counting of our various states and possibilities. Okay, let's see what happens in this case. So in this case, I cannot get rid of at least one of these spatial components. Because if you're moving, you have to have spatial momentum. So what we can do is we can put all the momentum along any direction. Okay, so in this case I put it along the x direction. Right? This is E over C, this is E over C. This is actually px, but the reason I wrote these the same is because I know that p mu has to be what for a massless particle? It has to be 0. I heard somebody whisper it. Okay, what is p mu always? It's m squared c squared, and the mass is 0, so this has got to be 0. So this is the simplest way of writing something that I know squares to 0. Okay? Now, what transformations can I do which won't screw this thing up, which won't change it? Yeah, I can do rotations in 2D. That's all I'm allowed to do. Okay? You following me? If the particle has mass, you can always go to the rest frame, and then you get 3D rotations that you can use to reorient. Okay? But if the particle is massless, then the momentum has to at least have this form, which means you only have 2D rotations you can do. Yeah?
Why does the 2D rotations a requirement? Because I guess I'm thinking like if you put E over C in any of those spots and like put it through the metric, you're still going to get 0, right?
If you put E over C in any of these spots?
Right. Like would that not be sort of how it would do? Like and then did P mu, you'd still get them canceling?
Yeah, but they're going to satisfy this no matter what.
Okay.
But you have to have the P mu vector itself. All of these components remain unchanged.
Okay.
And this is the point. Like if I do a 3x3 or a 4x4 rotation matrix, which is only non-trivial in the lower 3x3, I can do anything I want to this, and I'm still going to get this exact same thing back because everything's playing with 0. Likewise here, anything can play with these 2 zeros and it won't change it.
Gotcha.
Okay? All right. Now, the reason I'm showing you this is because I would like to unearth this interesting fact that when things are massless, their helicity is fixed. Okay? So in 3D, again, if I have a spinner which is positive, I can do a rotation and I can get the z-axis down. And that transforms the spin into a negative state. Okay? This is the same argument. Oh, I made it right there. I could have just pointed to that. Anyway. In 2D, however, so why? All right. If I rotate the y and z, can I negate this? No. Okay? Doesn't matter what I do. It's always going to point in the same direction. Okay? So again, this is just a reflection of the fact that the Wigner classification system, you know, this argument about, oh, if you're massless, you have to have this momentum, which means you only get a 2D rotation, is in sync with this notion. So this is a rotational argument. This is a boosting argument, but they mean the same thing. Okay? And again, the helicity of a massless particle cannot be changed. That's the takeaway from this. Whereas the helicity of a massive particle can be swapped. All right? Yeah, no. So, there we go. Yeah. Okay. So now, what I want to spend the last 15 minutes doing, Jesus Christ, is asking, okay, is all of this in the Dirac equation? I mean, you know, it's the, you know, I wrote down a solution to the Dirac equation. It was weird. It involved, you know, we did the rest solutions, and then we did the moving solutions, and then I showed you how SZ acts on it, and then I showed you how SP acts on it, where SP is the helicity spin component. What about, you know, how does this all play out in the Dirac equation? So let's go back to Dirac. And we are unfortunately going to be sold a new idea. Okay. So recall, a boost on spinors is generated by matrices in this form. Okay. And a rotation on spinors is generated by things in this form. Okay? Now what we're going to do is we're going to take our 4-component spinor psi and we're going to break it up into these 2 pieces. We're going to call this psi plus and psi minus. All right? Now how do psi plus and psi minus transform under boosts comparatively?
Psi minus equals a negative.
Yeah, oppositely. You know, there's a sign difference. And then under rotations, they're the same. Okay? So we're going to call these 2-component spinors Weyl spinors or chiral spinors. Okay? All right. Now, and this is just the psi 1, the psi 2 components. This is the psi 3 and the psi 4 components. These describe particles, these describe antiparticles. But this definition is going to prove valuable in just a moment. Okay, so let's remember that the adjoint spinor is given by I psi dagger gamma 0. Okay, we had to put in this gamma 0 to form the adjoint because if you wanted to form an invariant, then you had this interesting thing which you proved in your homework last time, that the gamma 0 is what comes along and saves you because the generator matrices are not all Hermitian. Okay? So gamma 0, we know what gamma 0 is, we wrote that earlier. So for psi, we find that psi bar, and psi is written this way, psi bar is actually equal to psi minus dagger psi plus dagger. Okay? So the psi bar, the multiplication by I and gamma 0, interchanges these two. Okay? So if we go back and we consider the Dirac Lagrangian, this is the thing that gave us the Dirac equation, then this originally took the following form: h bar c psi bar gamma mu d mu psi plus mc squared psi bar psi. Okay? So you should vaguely remember this. And all I want to do is I want to write this in terms of psi plus and psi minus. These are 4-component spinors, okay? And I just want to break this down in terms of psi plus and psi minus, okay? So here we go. Where by sigma mu, I have in mind, sigma mu has how many components? 4. Mu always runs from 0 to 3. So this is going to be the identity for the 0 component, and then sigma I, these are just the Pauli matrices, and we only have x, y, z of them. So the spatial parts are going to be sigma i's. And sigma bar is going to be I negative sigma I. Okay? Now, I mean, you guys can do this, you know, you just have to put in your gamma, because the gammas are expressed in terms of the sigmas. It's pretty straightforward. You plug in this for sigma bar, or psi bar, you plug in this for psi, you multiply all the matrices out, and you end up with this, okay? Does anybody notice anything interesting about this? Anybody notice anything interesting about this? I wish someone would raise their hand and tell me something interesting about this. Damn you guys!
I think Josh Lewis is volunteering.
Yeah, Josh! You can always phone a friend and Ross.
Doesn't look like a constant.
What'd you say?
It doesn't look like a, oh no!
No, it's not a constant.
Ross.
Okay. So I'm not sure. So I'm not sure if this is what everybody else is noticing. But the thing which I'm noticing about this is that if we set our mass to 0, then our Weyl fermions decouple.
Yes. Look, this is psi minus and psi minus. This is psi plus and psi plus. But this is psi minus, psi plus, psi minus. If I set m equal to 0, then this is the sum of two differential equations. Or sorry, this is the sum of two Lagrangians, and then you can vary them and you'll get a differential equation. But if I set m equals to 0, I can get a differential equation for psi minus and a separate differential equation for psi plus. And those two differential equations are not coupled at all. Psi plus does not appear in the psi minus equation. But if m is not equal to 0, and I write down the psi plus differential equation, it will involve a psi minus term because of this. Because you know, part of it is, if you want to find the psi plus equation, you take the derivative with respect to psi plus, which means you're going to get psi minus left over. Okay? So for m equals 0, we can work with only psi plus or psi minus. We don't need a 4-component spinor. Everybody follow that? Yes.
Why do you have an or, none, and there?
Or none and where?
Yeah, why would you only need to look at one of them?
Or makes sense there.
Wait, say it again?
Well, so why would you look at one and not the other? Why wouldn't you look at both?
So we could say, yeah, I mean, that's a really good question. So, it's kind of like saying, it's kind of like oh, wait a minute, hold on. This is kind of like helicity, right? Helicity, we normally have, you know, we have to be able to rotate this between plus or minus h bar over 2. So, you know, we have a positive helicity eigenstate, we have a negative helicity eigenstate, and we can, you know, by boosting, we can shift between them. So if the particle has mass, then you can never really say, I have a positive helicity particle, and that's, you know, well defined. But if you have a massless particle, you can literally define a positive helicity state, and negative helicity never enters the expression. You don't have the degrees of freedom that you have when you have a massive particle, because in a massive particle, it's got two states of helicity, positive and negative. But if you have a massless particle, it's only got one state of helicity, and that's it. And we're finding the same very similar thing here. If the particle is massless, I can choose just to work with psi minus. It reduces the degrees of freedom because you go from 4 to 2. Okay? Or I can choose to work with psi plus. I could, of course, work with both of them, even if m is 0. But they don't interact with each other. There's no, I mean, you just got two particles which look identical. One has psi plus and one has psi minus. Well, why don't you treat them as separate particles? Okay? That's if m is equal to 0. If m is not equal to 0, then these things, if you could start out with a state with only psi plus being non-zero. But the evolution of it, it goes to the drumming, but the evolution of it, because the psi plus, psi minus terms are here, the evolution of it will generate a psi minus contribution. Yeah.
So for massive particles, this still kind of implies like calling the plus and minus case distinct particles, like we argued in the massive term, or is that just because of the way we wrote this?
Wait, ask that one more time.
Okay, so when we said that like the chirality, or the helicity is either positive or negative, so you can call them distinct particles for a
Yes.
massless case. You wrote this with mass, so if you had a massive particle, that still sort of implies a separate plus minus, just that they're interacting.
Yeah.
So do we still define like two wholly distinct particles? for
If
that?
m is 0.
So I'm asking if m is not 0, do we still define two
No.
wholly distinct
No,
particles?
no,
Okay.
no. Okay? We good? All right, so here's what's really cool. When I defined psi plus and psi minus, I was defining the chirality of a spinor. And it's natural to think that the chirality of a spinor is the same thing as the helicity of a spinor. They have all this in common, but in general, no. They're not the same, okay? So let me just very quickly run you through an example so you'll see that they're not the same, unless m is equal to 0. And if m is equal to 0, then they are the same, okay? So psi 1, which is a e to the I p mu x mu, or h bar times e over mc squared. And we're going to do this in general first, and then we'll simplify it. Okay, so we're going to first of all choose our momentum to be along the z direction so that we can talk about helicity, and we all know what this turns the spinor into. Wow, they're really loud over there.
Those cheeses are people, they're loud. Those cheeses. I'm just gonna assume it's like this because it sounds like.
I could put p or pz here. All of the momentum is in the z direction, so you might as well just use the symbol p. Okay, now here's the interesting observation. You ready? Everybody ready? Is this an eigenstate of SZ? What's the eigenvalue?
H bar over 2.
It's h bar over 2. Are you ready? Yes. Is this a state of pure chirality? That means it's only psi plus or it's only psi minus? No. Everybody see that? Because you've got this and you've got this. Look, if I had just if I had non-zero things here and zero things here, that would be a state of psi plus chirality. Or if I had two non-zero things here and zeros up here, that'd be a state of psi minus chirality. But no, this has got this in bed with this. It's not a state of separated chiralities. But we wouldn't expect that, right? Because this thing has what? Mass. So let's see what happens. What miracle happens if we take the mass to 0? Okay? Let me remind you before you shit your pants.
Too late.
Oh my God, you guys. Okay, I see everybody getting nervous. This is m, that's division by 0. But let me remind you that every particle must obey this relationship. And when it's 0, that's 0. This, of course, means that E is equal to PC. You plug it in, this thing becomes 0, 0, 1, 0. Oh, sorry, this was, I meant to write this as the helicity operator, not the SZ, although they're the same because the direction of motion is in the Z direction, but I want to stress this is the helicity operator. Okay, same expression, okay? Is this an eigenspinor of the helicity operator? Yeah. Of course it is. Is it one of these?
Yeah.
Yes. Okay? So for massless particles, chirality and helicity mean the same thing. For massive particles, chirality and helicity mean different things. Okay? So to finish up, I'll just give you a definition and then send you on your way. You going? We'll go. It's fine. It's fine. Okay. Shh. I'm just going to finish up. So everything that I've talked about, if you think about it, has hung on our particular version of the gammas. And when I introduced the gammas to you, one of the things that I said was, this is not the only version of gammas you can have, okay? The gammas can take many different forms. Ours are particularly simple because you have these block diagonal forms, okay, that the gammas take. And that is a big part of this story of this thing breaking up into two pieces, and in the massless limit things don't mix. And you might worry or wonder, at least, wonder is a more positive way to think about it, you might wonder whether all of this splitting shit happens if you use a more arbitrary form of the gamma matrices, where they don't take this block diagonal form. And, well, there's just one thing you got to change in your story. Okay? The one thing you got to change in your story is, if you're going to abandon the nice block diagonal structure of the gammas that are in the version we use, if you're going to abandon that, then you've got to abandon this, where you say psi plus is the top two terms and psi minus is the bottom two terms. But you can still define chirality. You're just going to have to define these terms in some other manner. And so I'm going to give that to you. You can take a spinor in an arbitrary use of the gammas, and you can project it onto positive and negative chirality states using the following projection operator. 1 plus or minus, what do you think?
Gamma 5.
Gamma 5.
Yeah.
How's gamma 5 defined? Gamma 5 is defined as minus I, gamma 0, gamma 1, gamma 2, gamma 3. Obviously, if I change the versions of my gammas, it changes gamma 5, but this expression still works. Okay? All right. So in our current thing, gamma 5 takes the form of just 1, 0, 0, minus 1. And so you should be able to look at this projection operator, use this form of gamma 5. Okay, so let's just do this real quick. Let's see what the plus looks like. 1/2, 1 plus gamma 5. What does it look like? 2, 0, 0, 0. The 2's cancel. 1, 0, 0, 0. If I hit a spinner with it, which component is it going to return me? Psi plus. These are 4x4 matrices, folks. Everybody follow? Okay? But this definition works no matter what convention we use for our gamma matrices. So this is really the way you want to define chirality. You don't want to say it's the top two or the bottom two. You want to use this projection by gamma 5. Okay? Any questions? Yeah.
So does that sort of imply like an interchangeableness between the plus and minus components, or it's just saying that they would be in different spots? Because we're saying like the first and second component are the plus, the third and fourth are the minus. Are you saying that we're like actually interchanging them or just reordering them essentially?
You can do lots of different things. Yeah, it's going to be way more than just interchanging them. I mean, you can actually get a contribution to psi plus from all 4 components, and a different contribution to psi minus from all 4 components. It's only with this particular choice of the gamma matrices that you only get psi plus contributions from the top 2 and psi minus from the bottom 2. All right, any other questions? We're done, so you guys are free to go. Remember, you got a quiz Thursday. The homework that you might have looked at beforehand, although most of you haven't, is really based on this discussion. So,
When's our midterm?
oh yeah. When's your midterm?
Tomorrow.
No. Sorry, your midterm is. Hold on. So March 6th. There's a Thursday right around March 6th, and that's when your midterm is.
That's during March meeting.
Yeah, it's during March meeting.
Okay.
So take your midterm during March meeting. All right, I'm gonna turn the camera on. Huh?